An S-shaped tetromino is obtained by attaching 2 by 1 horizontal dominoes along their long sides, such that the midpoint of the long side of one domino is the corner of the other one. Another type of tetromino is obtained by rotating the S-tetrominoes, and by reflecting our 2 obtained tetrominoes through a horizontal line, we obtain another 2 types of tetrominoes. These all 4 types together define all the tetrominoes in our family. A lattice polygon P is, by definition, a finite union of unit dominoes, and it is also uniquely defined by its interior and exterior perimeters. For example, the perimeter in the illustration defines the following lattice polygon P. A lattice polygon P has a tiling, if it can be tiled by tetrominoes in our family. The polygon P, which was given previously, has, for example, the following tiling. However, this lattice polygon has also the following different tiling by tetrominoes in our family. Let us check now the following polygon P. This polygon has the following tiling. Another tiling of P by tetrominoes is the following. In conclusion, we see that a lattice polygon P might have more than one tiling. This leads us to the following main question in this challenge. The main problem. For a lattice polygon P, prove that for every tiling of P by tetrominoes, the parity of the number of each type of tetromino in the tiling depends only on P. In other words, for each tiling of P, the parity of the number of each of our 4 types of tetrominoes will be the same for every other tiling of P. For example, let us look again at the tiling of the previous lattice polygon P. For this tiling, the number of red tetrominoes is odd, the number of yellow tetrominoes is even, the number of blue tetrominoes is odd, and the number of pink tetrominoes is even. Let us look at the other tiling of P. Again, the number of red, yellow, blue and pink tetrominoes is respectively odd, even, odd, and again even. Our main assertion implies that for every other tiling of P, the parities will always be odd, even, odd and then even. Our goal is to prove that the parities of the number of tetrominoes depend only on P, in the general case, for any random lattice polygon P. To prove this, let us consider an infinite grid of unit dominoes. And let us consider a lattice polygon P in this grid, such that P has at least one tiling. Now, let us create a coordinate system, such that our polygon P is inside its first quadrant. We start by showing that our red tetromino has the same parity for every tiling of P. For this, let us start from the origin of our system, and let us number the first row of dominoes, from left to right, by 0, 1, 2, etc. Let us do the same for the second row, except that we start from number 1, and we take the negative sign. For the third row, we start from number 2, and take the positive sign. For the fourth row, we start from number 3, and take the negative sign. We can continue in this way, and fill all the dominoes in the first quadrant. Let us try now to find some information on the sum of the numbers in the dominoes, which are occupied by our lattice polygon P. Since P consists from the 4 types of the tetrominoes, let us check which sum each type of tetromino adds to the total sum in the dominoes which are occupied by P. It can be easily checked that the total sum of the numbers in the dominoes which are occupied either by the yellow, blue or pink tetrominoes is equal to 0. However, each red tetromino adds 4, or minus 4, to the total sum. This clearly implies that the total sum of the numbers in the dominoes, which are occupied by the polygon P, is divisible by 8, if, and only if the number of red tetrominoes is even. Hence, if, for example, in one tilling the number of red tetrominoes is odd, that is, the total sum is not divisible by 8. Then, in any other tilling the total number of red tetrominoes cannot be even, since all the other type of tetrominoes do not contribute to the sum. And hence, if the number of red tetrominoes is even, then the total sum is divisible by 8. Which is a contradiction, since we assumed that it was not divisible by 8 at the previous tilling, and the total sum is the same for every tilling. Similarly, if the number of red tetrominoes is even, then we can show that it must be even in any other tilling. Thus, we proved that the parity of the red tetrominoes is the same for every tilling of P. To prove that the parity is the same for the other 3 tetrominoes, we can use the fact that they are obtained by the red tetromino by using a rotation and reflection. Thus, in order to use a coordinate system and a numbering for the other 3 tetrominoes in order to repeat the argument, which was used for the red tetromino, we just need to reflect, or rotate, or reflect and rotate, the original coordinate system and numbering correspondingly. Thus, we can prove that the parity is the same for all of our tetrominoes. Hence, we proved our main assertion, and thus our proof is finally complete.